Welcome to the afternoon track for today. Today we have Programming and Proving in Agda by Jesper Cockx. So I think it was 2 years ago or 3 years ago, we had Phil Wadler giving a keynote at Zurich, which he opened by saying that Agda is the language that Haskell would like to be when it grows up. So as an organizer thinking in the future, I thought so it'd be good to have a little introduction to Agda now, so that when Zurich does become an Agda conference 5 years from now, everyone knows what's happening. Good. Thank you very much, Jesper, for giving us this track. Jesper is an assistant professor at the TU Delft and one of the main contributors to Agda. Thank you very much.
Yeah, thank you for the introduction. And thanks for inviting me. I think it's really great to have this opportunity to talk about Agda for such a large audience of Haskell programmers. I had to think while preparing this presentation, well, what is the level I want to aim at? And so my main goal with this lecture is actually to introduce people who haven't heard of Agda at all, or have maybe heard of it but never used it, right? So I decided to base it on some of the lectures that I use also for my functional programming course in Delft, where most of the course is about Haskell, using Graham Hutton's book, Programming in Haskell, which you might have heard about or read. And then there's one chapter in that book where he talks about, the nice thing about Haskell is that you have pure functional programs, so you can reason about them in equational reasoning style. You can prove that your programs are correct. And I think that's absolutely great, and it's one of the very nice chapters in that book. But when I read that, I also thought, well, I mean, it's nice to write proofs on paper, but why can't we write these proofs in a proof assistant and actually have them be verified? And so that's the end goal I want to try to reach in today's lecture, is actually to show you how to write equational reasoning proofs about simple Haskell-like programs and prove them correct in Agda. Okay. And so to get there, there's a bit of a path we have to tread to get to the identity type and equational reasoning at the end. So I'll start with a bit of introduction, what Agda is, what goals are, what are dependent types. Then there's some part about, assuming you already know a bit of Haskell, well, what are actually the main differences, both on a syntactic level and also on the bit more theoretical level between Agda and Haskell. I'll talk a bit about what it means to have types as first-class values in Agda, and I think this is kind of really crucial difference between Agda and Haskell, is that in Agda there's not a separate type level or term level. So we'll look a bit into what that means. And then I'll go into, well, this main topic maybe that Agda is well known for is dependent types, dependent functions. And then in order to use these dependent types to do equational reasoning, we'll need one more concept, which is this Curry-Howard correspondence, which will allow us to write down our proofs in Agda and verify them just by type checking. So that's the plan for this next 2 hours. So let's start with the introduction. Let's start with a quote by famous Dutch computer scientist Dijkstra. He said, well, if we have, want to show that there's no bugs in our program, we can do testing, but this can only ever show the presence of our bugs, and it can never show the absence of the bugs. So if we want to show actually that there's no bugs in our program, we have to turn to different techniques. And so, well, what kind of different techniques are these? Well, the broad collective noun for that is formal verification. And one particular form of formal verification are these dependent type systems. So what is a nice part about dependent types is, well, it's a formal verification that is actually embedded in our language. So you don't have to learn any new syntax or new tools or install any new tools. You get a very tight integration between the IDE and the type system. We'll see a bit of that soon. You can use it to express invariants of your programs or properties of your programs directly in the types. And yeah, you can use the same syntax for programming and proving, so you don't have to learn a new syntax for it. And my motto here is, well, that formally verifying the correctness of a piece of software ideally should not be any more difficult than writing it in the first place. So I'm not sure if we're quite there yet. So there's some things that are still more difficult, but I'll let you be the judge of that. Okay. And then that leads us to Agda, right? So Agda is such a language that fully embraces the concept of dependent types. But at its core, it's just a purely functional programming language, quite similar to Haskell in many respects. Yeah, so what sets it apart from Haskell is mainly support for dependent types. And also it's also quite well known for the support that it has for interactive programming. So that means that, well, you can actually write your programs in a kind of conversation with your type checker, and the type checker can help you while you're writing the program to stepwise construct your program. Okay. Yeah, then a bit of practical stuff, right? If you want to follow along with the examples in these slides, and I'll switch to editor later on also. You can do so. I think the most accessible way nowadays to install Agda is either, well, depends if you're on some Ubuntu derivative, you can opt to install Agda. Otherwise, you'll probably have either Cabal or Stack installed, since you're here at Zurich Hack, so you can just install it from source. It's on Hackage. And then, yeah, I'll be using the VS Code plugin. There's also, I mean, the Emacs plugin and a few other editors. Yeah. The nice thing about the VS Code plugin, that in theory it has this option that you can enable the Agda language server, and it will automatically download an executable for you. So you don't even need to have an Agda installed. In practice, it's sometimes a bit flaky, so if that doesn't work, well, try one of the other ways. Yeah. Okay. And then, yeah, if you actually want to get a full interactive experience with Agda, you'll have to install well, some plugin for the editor that you're using. I think the ones that I'm aware of existing, I think VS Code and Emacs are the most well-supported ones, and there's also packages for Atom or for Vim, if you prefer one of those. Okay. I think Emacs was historically the one that's best supported, but yeah, VS Code is getting up there now. Okay. Okay, and then let's take a look at a first Agda program. So here's a very small Agda program where we're defining a data type, right? It's called greeting. It has a single constructor called hello. And then we're defining a function called greet that returns something of type greeting. And the thing it returns is this constructor hello, right? So, yeah, so this is, I think you can think of the equivalent Haskell program, right? It would say, I guess, data greeting equals hello, and then the function greet would be, well, basically the same. Well, okay, so maybe you can help me also, so I can ask for some answers, right? So what are the differences you spot between this and the thing you would write in Haskell? Yeah. It uses GADT syntax, indeed. So the GADT syntax is the default way to define data types, or the only way to define data types in Agda. So indeed, you have to actually specify the return type of each constructor and not just the types of its arguments. Yeah. Yes, indeed. So the other thing, well, we have to, well, what would be in Haskell? This would be a sort annotation. So we have to annotate what, or a kind annotation. We have to annotate what type does greeting belong to, and in this case, that's called set, which is the equivalent in Agda of star or type in Haskell. One more. Very good indeed. So that's, I think, a mistake in Haskell, and I think it's a bit hard to fix now, but Agda does not make this mistake, and it uses the single colon for typing. And you'll see later it uses a double colon for list cons. Yes.
Constructor doesn't have to be uppercase.
Very good. So that's another one, is that the constructor here has a lowercase h, so it does. So there's less restrictions on what kind of names have to be of an uppercase or lowercase. Yeah. Or no restrictions, basically. Yeah. Is there a convention? Yeah, so the convention that the standard library follows, and that will also follow here, is that that if something is like a data types will be with capital letters, values or functions that return the value will have a small letter. Yes, but so including constructors, which are values, right? They're not types. Yeah.
So how do you print?
How do you print? Yeah. Well, that's a good question. I'm not going to answer it here. But so you can you install the standard library. You import the I/O module, which gives you the foreign function interface bindings to the I/O monad in Haskell, and you can use that to print. So we don't have our own proper I/O support. Well, there are some definitions in the standard library, but they're just bindings to the corresponding Haskell definitions. Yeah. Okay. Good. So, and then the nice thing we can do now, we can, and let me actually switch to VS Code. But so we can now load this file in our editor and start using some of the interactive commands. So here's my Zuri hack, and sorry, I should have prepared this better. Okay. Yes. So, I mean, I've loaded this file already, but I'll reload it now. So what I'm doing is pressing Ctrl-C, Ctrl-L, and then you'll see you get all the nice syntax highlighting. This syntax highlighting is actually type-based, so you'll see that, I mean, even though greet and hello are the same syntactic class, the hello will get a green because it's a constructor. Right. So that's based on the kind of the definition of hello in this case. And then we can now ask Agda things about this. So we can press Ctrl-C, Ctrl-N. Then you'll get a prompt here at the bottom asking you to what do you want to normalize. So for example, I can ask, can you normalize greet for me? That gives me hello. The other command I wanted to show is there's Ctrl-C, Ctrl-D for a deduce type or infer type. And then we can give it some expressions. So we can say, for example, this goodbye. What was that? And then infer type of goodbye is greeting. Okay. So these are just two commands. We'll get back to the editor later, and then we'll see a couple more commands. But for now, okay, that's what we can do. Yes.
How do you enable the Agda mode? Save the file with an extension?
Yes. So, but yeah, if you have the Agda mode installed, then it should automatically switch to Agda mode. Otherwise, you can always select language mode here and say, well, I want the Agda mode. And then.
Right. I mean, I created something from scratch. I don't have that file on this thing.
Yeah, you can create a file with a .agda extension. Yes. I mean, I think I have a few imports here at the top, but I mean, you don't need those for this example. Yeah. Okay. I'll come back to the code a bit later. A few more slides I wanted to show. So let's dive a bit more. So we saw a few syntactic differences, but let's dive a bit more into the differences between Agda and Haskell. So first, yeah, a few of the syntactic differences that we already noticed is typing uses a single colon instead of a double one. Naming has fewer restrictions, so you can use any name starting with a small or capital letter at either type or term level, and you can have symbols occur in names. In particular, that also means that you have to use white space more often than in Haskell. So, for example, the string 1 + 1 without spaces, that would be a valid name for a function in Agda, or for a constructor, or for a type, which means that if you want to actually apply the plus function to two arguments 1 and 1, you have to write spaces around the plus. So you have to write this. Yes. I think, something that sometimes tricks up newcomers to Agda. And then also one small difference is that if you want to refer to an infix operator without providing the arguments, then we write, well, in Haskell you would write parentheses around it. In Agda, we write underscores instead to indicate where the arguments should go. Okay. So if you want to refer to plus by itself without the arguments, you write underscore plus underscore. And this is without spaces, right? Okay. Then, well, something else that's not really a difference between the languages, because Haskell also allows Unicode syntax, but in Agda it tends to get used more often. So in particular, there's a few symbols, so you can use the Unicode arrow instead of dash greater than. You can use the actual Unicode lambda instead of a backslash. There's some symbols that are very conventionally used in Agda programs to indicate certain types and terms. So these are some of the ones that I'll use in this tutorial. Okay. And so because they're used so commonly, there's also in the Agda mode there is some built-in support for entering these using LaTeX syntax. So for example, if you want to write an arrow, then you can write \2 and then the Agda mode will replace that with the arrow. So here I want to write this function again, well, so write \L. And then here actually, so the Agda mode will show you all the symbols that you could mean, right? So if I just continue typing, I write lambda. If you make a typo, then you have to start over again. But if you don't make a typo, then you get the Unicode lambda. And then for 2, so the other thing is now I write 2. Now it still has these 3 dots under it. So I have to actually write space to accept the symbol, or write something else that's not a continuation of the sequence. Okay. Yes.
Just a minor remark, but I think in Emacs you don't need to start all over again if you mistake. Just erase.
Okay, yes, so that might be a different, yeah, so sorry, I have to repeat the question, by the way, I remember. So there was a remark that in Emacs you don't have to restart the sequence if you make a mistake. So quick quiz question to see if you're paying attention. So here's 4 names that you would maybe want to use or not want to use for an Agda function. So the question is, well, one of those 4 is not a valid Agda name. Which one is it? And so who thinks is I see people raising, yeah, there are. So who thinks is the first one? Who thinks is the second one? I think this is the third one. No, the fourth one. Okay, everyone very good. So the second one indeed has a space in the middle, which means that's, I mean, those are two names, right? This is a function application of foo2bar. This is not a single name, but all the others are, in fact, valid names. And I mean, I have seen all of them actually being used as in real-world Agda code. So whether that's good or not, I don't know. But okay. So yeah, next we can define data types. I already showed you how. So the difference here is with we have to use the GADT syntax, and we have to specify that the type we're defining is in set or is in some other type. A bit more about that later. For natural numbers, we can also define them as unary natural numbers, right? So either we have 0 or we have a successor of another number. And then Agda does have a bit of a built-in support for natural numbers, so you can use this built-in natural pragma to say, well, this is my type of natural numbers, and then Agda allows you to write the decimal syntax for it, right, rather than using the 0 and successor constructors. And then if we want to define functions, well, just as in Haskell, we can use pattern matching, so we can define, for example, the not function in this way. I think pretty straightforward. Or we can define functions on pattern matching on natural numbers, like with deeper patterns here. Right? So this can be nested. And we can also make recursive calls, right? So here we're making recursive call to is even x. And so for plus here, well, we can define it. So if we want it to be infix, we have to write the underscores in the name. And then in the actual clauses of the definition, we can just use it as an infix notation. Right. Okay. And then once we've defined this, now we can actually define this here. And now we can normalize if we want to compute 2 plus 2, then with this definition of plus, Agda will say, well, this is 4, which is really the 4 successors applied to 0. Okay.
So on the left-hand side of the second equation,
yes,
you put brackets around sub x. Are brackets necessary?
That's a good question. I don't think so. I just wanted to make it, yeah, no, they're not necessary. I just wanted to make it clearer because, so I'm using this infix declaration here also, which means that I can write things like x plus y plus z without writing parentheses, and it will automatically associate to the right because of infix or. Good. Good. And then, okay, so now comes the exciting part, interactive programming. So if you want to use some kind of interactive programming, you write a hole in your program, which can be created by writing a question mark or this curly braces bang bang thing. And then once we have load our file with a hole in it, we get access to new commands. So there's this Ctrl-C, Ctrl-, which gives you the information about the hole. Ctrl-C, Ctrl-C, which allows you to do a case split on a variable. So I'll show you what that does there. And Ctrl-C, Ctrl-space will fill in the hole with a given solution. So let's actually show you how this works with this, and let's define a maximum function on natural numbers, which I've put here, and I put the commands here again in the comments so you can follow along. Right, so how do they define a maximum function? Well, we'll have to do some kind of pattern matching first, right? And instead of writing out the cases by hand, I can say, well, there's this variable x here. I want to get the different cases for x. And then I do Ctrl-C, Ctrl-C for the case split, and Agda will generate all the possible cases for x for me. And then, so now we know maximum of 0 and y. Well, we know what that is. That's not going to be 0, so it's probably y. So we write that in the hole, and then you can write Ctrl-C, Ctrl-space, which will type check that the solution has the correct type, and then if it has the correct type, it will fill it in. If I had instead written something like true, which is not the right type, then you would get a type error here that bool is not equal to not. This should be read as not equal to. Okay. Right. And then here in the second case, well, we have to do some more case splitting, right? We have to see, well, if y is 0, well, then it's going to be the first argument, which is successor x. And in the final case, well, we have to take the successor of the maximum of x and y. Oh yeah, I can also show you, well, so suppose I know, well, this is a successor of something, but I don't know what yet. Well, I can already take one step by just saying, well, let's take the successor constructor, apply to question mark, and then Agda will generate a new hole for the question mark. And then now we can say maximum of 2 arguments. So again, you get now 2 holes, and then finally we can fill these in. So you can get a very gradual step-by-step construction of your program, and the type checker will check at each step that what you've written so far is correct. That makes sense. Yes. Okay, let's go back then. Then let's head a bit into some more of the differences between Agda and Haskell on a more semantic level, or more more fundamental differences between the type systems. And so I think the biggest difference in a sense here is that Agda is, in contrast to Haskell, is a total language. And what does that mean? Well, that it's extra pure, so it allows even fewer side effects than Haskell. In particular, there's no runtime errors or exceptions that can be thrown. There's no error function or no undefined function. You cannot write incomplete pattern matches. So there's always the warning for incomplete pattern matches is also always on, and it's always an error. And you cannot write non-terminating functions. And this is, I think, the biggest conceptual difference to get around. So, so we'll see a bit about how Agda enforces this. So what this means is that all functions written in Agda are really functions in a mathematical sense, in that they map each input to an output, and they do so in finite time. Right? You cannot go into an infinite loop, which is a nice property to have. Okay. So why is this nice? Well, it's nice as a developer, knowing that, well, your program doesn't contain missing cases, doesn't go into an infinite loop. It's also nice for refactoring your programs, because you know, well, you're not accidentally not accidentally missing one of the cases when you edit a new constructor, for example. And, well, there's less need to document valid inputs, because in principle all inputs are valid, or at least all of them will produce some result, none will throw an error. And then later on we'll also see that actually totality is crucial, really, if you want to have proper support for dependent types and proof, the proof assistant features of Agda. We'll get to that. Okay. Yes. So, okay, let's dive a bit deeper into how Agda enforces totality. Well, it has 2 checks to enforce totality. First, there's a coverage check, right? So this is maybe somewhat well known if you're from Haskell, and you can enable this in GHE as well, right? And if you write an incomplete definition like this, well, you will get an error saying that you missed the case for pred of 0. And similar to that, Agda also has a termination check built in, and this will rule out any definitions where Agda is not sure that they are terminating. So, for example, if you write some infinite natural number that computes to 1 plus inf x, well, then the termination checker will catch this and not allow this function. This does also mean that, well, sometimes there is functions that are terminating, but Agda doesn't see so, because the termination is kind of subtle or in a roundabout way. So Agda uses a very simple, somewhat simple structural recursion principle, right? So in each recursive call, there has to be some argument that gets smaller. Or there can be two arguments that get smaller in the lexicographic ordering, but I don't want to go too much into that. But basically, if there's some recursive calls in which the arguments get bigger and in others where it gets smaller again, then Agda will reject the function, even if it turns out to be terminating in the end. Yes.
Is there an escape hatch like Idris has a similar system and
Yes.
it has two functions, a search total and a search smaller when the termination checker itself
Absolutely.
cannot see it?
Yes, so if I really want to write this function, something like this. Oh. Right, now I get termination check failure, but I can, if I say, well, this is terminating, then the termination checker will shut up and just allow me to write this definition.
Is it possible to use this on the inside of the function or just for the whole function?
For the whole function. And actually it applies to a whole mutual block of functions. So if you have mutually defined functions, it applies to the whole set of mutually defined functions. Yeah. You can also say that it's non-terminating, which would be a bit more honest in this case, which, I mean, then the difference is that Agda will then not evaluate this function during type checking. Okay, yes.
Can you express
Sorry?
Can you express the Ackermann function in Agda?
Can you express the Ackermann function in Agda? That's a good question. I'm pretty sure you can, because it's still, I mean, it's using a lexicographic ordering, basically. I mean, I would have to try. Let's try it later. But I think, yes. I think there should not be a problem. Yeah. Hmm? Yeah. Yes?
Is there also support for co-recursion?
Is there support for co-recursion? Yes. So you can define co-inductive record types, which are potentially infinite data structures, right? And then there is a separate productivity checker that checks if they will not be terminating anymore, but you still have to be productive, so they always produce the next bit of output in finite time. Yeah. Yes?
So you showed us that you want to define the thread function.
Yes.
But Agda's going to say thread 0 is not defined.
Yes.
So what do you want to define? What would you recommend one does in that case?
So the question is, what would I recommend if you want to define a pred function? Well, it's a partial function, so you could use maybe as the output. That's one option. The other option would be to actually express the invariant that the output has to, the input has to be non-zero, right? So then you would take as inputs a number plus a proof that it's not zero, and that it would produce just a natural number as the output.
And that second choice would then require perhaps doing quite a lot of proofs.
That's, well, not that much proving in this case. I think, maybe at the second half of the lecture I can show you how to define it. Yeah. But it should be pretty easy. Yeah.
Do you have a preference between those two things in general? What is usually?
Often you need both. You need both of them, right? So if you already checked the invariant, then you should keep around the proof that it's not zero, right? And then you can use that version. If you get some user input, well, you really don't know whether it's zero or not, so you have to deal somehow with the case where it's zero, and then the maybe version will do the sensible thing, which is, well, you have to deal with that case separately where it's not defined.
But the answer might be tempting. It might just be to define thread 0 is 0. That is returning the wrong answers.
Yes.
But that's really dangerous.
Yes. Yeah, so that's, I agree. So defining pred 0 equals 0, well, that's another option in theory, but it's, then you have to be careful that that is really the function you wanted to define, right? And then you're really defining a different function then, yeah, I would say. Yeah.
One more question.
Yes.
So I assume that you can only express primitive recursive or structurally recursive functions in this way. Is it possible to define a measure function or an arbitrary
Yes, so the question is, can you define a measure function? So, well, yes, in the standard library, there is a definition of accessibility proofs and well-founded relations. So you can define your own relation, prove that it's well-founded, and you can do recursion over that relation. I mean, there's a fixed point operation for that. So it's a bit more verbose than the built-in termination checker, but you can absolutely do it, yes. Okay, let me continue then. Oh, no, one more question, yes. Yeah. Okay. Okay, cool. So the Ackermann function is on Discord if you want to. Great. So let's look into some fun things we can do. So in Agda, there's no distinction between the term level and the type level. And in particular, that means that types such as not or bool arrow bool are themselves just terms. And in particular, they are given this type set. Right? So there are terms belonging to this type set. And this set is more or less just a type like any other type. So we can pass them around as values. We can return them. We can define functions. Like we can have set as a return thing. So for example, if you want to define a type alias in Agda, well, we don't need a separate type keyword like in Haskell. We can just define a function that returns the value of type set, and then use that function in the type of some other function. So just one small way in which not having this distinction simplifies things. Okay. Then another thing that Agda uses this set type for is to define polymorphic functions. So again, in Haskell, we have a separate concept of polymorphic functions. In Agda, well, this is kind of just a function, just another kind of function. So for example, if we want to define the identity function polymorphically, well, we define a function that takes a type A as argument, and then an argument of type A and returns a value of type A. And the function is defined like this, right? It kind of ignores the first argument, it's just there for typing, and then just returns the second one. And then we can apply it to not to get the identity function at not. We can apply it to bool to get the identity function at bool. Yes, a question.
Can you mark the A as erased so I can have pattern match on it?
The question is, can we mark A as erased so we cannot pattern match on it? So Agda does not allow pattern matching on set anyway, so you do not have to mark it as erased. It will be erased anyway by the compiler. But if there's other arguments that you want to erase, there is a feature for erasure annotations which you can use to mark things as erased explicitly. So of course, oh yes, another question.
Can you mark the type A as implicit?
That's my next slide. So of course it's very annoying to always write this type argument explicitly. So we want to infer it, and Agda can infer things, and you just have to ask it nicely. In particular, you have to write curly braces around the argument, and then it's marked as implicit, and it will do its best to infer it. Now, unfortunately for dependent types, there's no such algorithm as Hindley-Milner. So type inference in general is undecidable. So sometimes you will see that Agda cannot infer the argument, but in this case, it's pretty easy usually. So it will infer it. But you might get these unsolved meta variables if it cannot infer. Yes? Yes, if you want to use it explicitly, or give the argument explicitly, you just write between the ID and X, you write curly braces and you give the argument. Or you can give it also, you can give it by name by writing curly braces, A equals, and then the thing you want to give. Yes. If you have many implicit arguments, sometimes that's useful. Yes. More question? Yes. So question is there a distinction like between set and prop in Cock? Well, actually in Cock there is prop, there is set, and there is type. And so set in Agda really corresponds to what's type in Cock. And then we also have a prop universe in Agda, which corresponds to S-prop in Coq. And so we don't really have the equivalent of Coq's prop, which is impredicative, while Agda is a predicative language. But yeah. Yes.
Is set of type set?
Question is set of type set? No, set has type set1, and set1 has type set2, and etc. to omega. Yes. And then also Agda has a feature called universe polymorphism, so you can write functions that are polymorphic over the universe level. So you can, okay. But don't want to go into that too much here. Okay. So let's write something that you might already know from Haskell, which is the if then else. But the difference here is that we can just define if then else as a function, so it's not built-in syntax of Agda. It's just a function we can define like this. And so the way we define it is, well, using these underscores to indicate where the argument should go. Right? So if then else is a function with 3 arguments. One comes after the if, one comes after the then, one comes after the else. And to define it, we just pattern match on the Boolean. If it's true, then we return the first argument. If it's false, then we return the second one. And we can use it in like you would use any if-then-else operation in another language. And so this is an example of what's called a mix-fix operator, which is kind of a generalization of infix operators, where the arguments can come in any places. Yes, question.
So does Agda use lazy evaluation?
Does Agda use lazy evaluation? It uses lazy evaluation during type checking, yes. And then there's different backends that you can use, which can be lazy or strict depending on the backend. So the default backend is the GHE backend, which is lazy. There's also a JavaScript backend, which is strict.
So does that give you a strict
Yes, absolutely. If you're using the JavaScript backend, you should not use this if then else. Yes, then you should actually have an argument of, well, you should have tunked arguments for the then and the else branch. Yeah. Yeah.
So how efficient is this x less than or equal to 9,000 comparison with piano?
So the question is, yeah, how efficient is this less than or equal if you're using unary natural numbers? It's very inefficient. Luckily, there is more of these built-in pragmas that you can use to give it to Agda to use the built-in operations for these less than or equals. And then it will use the efficient implementation instead of the one that pattern matches on 0 and suck. But yeah, you do have to be careful when defining less than or equals. Yeah. Okay, more.
Is there a way to annotate programs or libraries about what backend it might be unsafe to compile with?
Question, is there a way to annotate which libraries are unsafe to compile with which backend? Not really. So, yeah, no, that might be a nice feature, but I don't think there's a way to do that. Yeah.
This is a silly question, but if everything terminates, does it make a difference what backend?
The question is, if everything terminates, does it matter whether we use a strict or a lazy backend? Well, it will terminate, right? But for if-then-else, we really don't want to use strict evaluation, or for this definition of if-then-else, we don't want to use strict evaluation because that would mean we always evaluate both branches of the if-then-else, which, I mean, in general, even if it terminates, you don't want to do that. Especially if one of them contains a recursive call that is a recipe for disaster. Yes. Okay. Okay. So just as we can define polymorphic functions, we can define polymorphic data types by parameterizing them over something of type set. So for example, here's the list type. So you have the empty list, and we have the list cons, which uses the double colon and takes an argument of type A and a tail. And there's a new list. Unfortunately, there's no built-in support for list syntax in Agda, so you have to kind of write the lists in the ugly style with double colons in between. You get used to it, but okay. And just like that, we can also define a type of tuples. So since we don't have separate namespaces for types and terms, we have to kind of give a different name for the type here. Right? We cannot name both of them, comma. we can name one of them comma. That's a fine name for a constructor. But so at the type level, we use the Unicode cross symbol. So this is the times, because this is known as a product type also in type theory. And then we can define the first and second projections of it. Okay. And then, like I said before, it's not allowed to pattern match on types, so this is not a valid function. If you write this in Agda, actually, well, it will not recognize bool as being a pattern. It will just think bool is a name of a pattern variable, right? So this will be, I mean, it will be accepted, but it will be a constant function that always returns not, and the second class will be marked as redundant. Yeah. And one reason why this is not actually accepted to pattern match on it is that, well, just like Haskell, all types are erased during compilation, so there's no trace of them left at runtime. Yes. Yes, indeed. Yes. So Agda does not have a direct equivalent of type families. So you can define your own universes on which you can pattern match, right? So you define your own data types that represent a subset of all types, and then write a function that interprets these terms in the universe as actual Agda types. So that's the usual way to work around it, or to define these kind of things in Agda, yes. Or you would use type families in Haskell. Okay. Another quiz question for you. So here's a function, lookup function on lists. Right? We want to look up and the question is, well, is this a valid Agda function? Who thinks yes, it's a valid Agda function? Who thinks no, it's not a complete function? Yes. Who thinks it's not terminating? Who thinks there is some other reason why it's not valid? I think. Okay, so I think yes. So the second argument was the correct one. It's not complete because we're missing a case for the empty list, right? I mean, we have to, just like with the predecessor function, we have to actually decide what to do when this is given an empty list or when the number is bigger than the length of the list, right? And so now, of course, we could just add a maybe. That's one way to solve it, right? But we'll try to find a nicer way to actually encode or statically enforce that the inputs are well formed, that we actually know that there's no possibility that this index is out of bounds. Okay. And for that, we'll need dependent types. Okay. So dependent types are important concept in Agda, so let's look a bit more into them. And so I like to use an example. So there's one example that's always used for introducing dependent types, and I'll give it later on, but I don't like to start with it. So let me use an example instead that I used during my PhD defense. So I had all my friends and family there, so I had to come up with some fun examples. So I decided, well, let's implement a cooking assistant. Right, and we want to, well, I don't know, I'm not a very good cook, so let's assume you have 3 kinds of food that we can prepare. So we have pizza, we have cake, and we have bread. And we want to implement a function that tells us, well, how much cheese do we need to add to this food to make it taste nice. So there's a function from food to not. I'm not specifying the units here, but okay. But so there's a problem here, an obvious problem, which is that now when we implement this function, it has to be complete. In particular, we have to answer the question, well, how much cheese should we add to our cake? And this is like obviously a nonsensical question. So we shouldn't even like be able to consider the question, right? And so we want to express in our type system that this question should never be asked, right? Okay. So how do we do that? Well, one way to do it is by recognizing that actually there's 2 types of food, right? There's cheesy foods and there's chocolatey foods, and so this is a complete and a binary classification of all kinds of food, and they should never be mixed. So that's what we do here, right? We can define a data type of flavors. So you have a cheesy flavor and a chocolatey flavor. And then we define our data type of food. which is now no longer of type set, but it's a function from flavor to set. And what does that mean? That means that now each constructor has to specify which flavor does it have. Right? So for pizza, we can say, well, pizza is cheesy food, cake is chocolatey food. And bread, well, you could add cheese or chocolate on it, but you should never mix it. So we can say, well, bread, well, for any kind of flavor we can think of, well, we can get food with that flavor, but you have to choose one or the other. Right? And so now we have, well, this declaration defines a new type, food f, for each term f of type flavor. Okay? And so now if we want to, what's the nice thing now that we have defined it this way? Well, we can define our function called amount of cheese, right? Saying, well, this doesn't take an input of type food, but now it takes an input of type food of flavor cheesy. And we just define the two cases for pizza and for bread, and we leave out the case for cake. And magically, well, not magically, but because of the types that we defined, Agda will recognize this as being a complete function. And in particular, Agda knows that cake is not a valid input to this function anymore. Question? What about cheesecake? No, I refuse to acknowledge the existence of cheesecake. Next question, please. Yes.
Is it possible to solve this with using proof of inequality instead?
The question is this possible to use a proof of equality instead? Well, yes, but the equality type in Agda is also defined as an index data type, so yes. So you're still using index data types somewhere, yes.
Is this already an example really of dependent types, or is this still doable in Haskell using a GADT?
So I think you could still do this in Haskell with GADTs probably, and yeah, so I mean, I would say that GADTs are a kind of dependent types, it's just not full spectrum dependent types. So yes, so this is dependent types. I mean, food is clearly a dependent type, right? So okay, let's see. What is other dependent types actually? Well, these types invented by this guy Per Martin Löf in 1972. And so dependent types are just, well, are actually not a single type, but are families of types that are depending on some term of a base type, right? So in this example, which was not by Per Martin Löf, but by me, is food is a dependent type and it's indexed over this base type of flavors. So for each flavor, we get a different type of food of that flavor. And then, okay, so now I can't get around it. I have to introduce the type of vectors also. Oh, there's a question first. Yeah.
Just a comment on that.
Yes.
I would say that in GADTs, they are quite, in Haskell, they are quite dependent types because the parameter that you have to pass in GADT has to be a type.
Yes.
Here in Agda, it's a valid.
That's a good point, yes. So there's a difference between this and GADT is that the argument to food here is not a type, right? With GADT, it has to be something at the type level. Well, here flavor is really just like it's not a singleton or lifted data type or anything. It's just the type flavor, which is just the data type. Yes. Yes.
I have a question about your bread example. So suppose your bread type was not the one that you've given here. Suppose you gave bread an extra parameter for proof that F is not cheesy. How would that impact what you write in the definition on the following slide?
Well, then you would still have to deal with that proof somehow explicitly.
So you would have to consider the cheesy case.
Yes.
But then,
And then you can prove that that case is impossible, right? So there's something called, well, getting ahead of myself again a bit, but there's something called an absurd pattern which we can use to dismiss the cases that are impossible in our.
and should you use it in this case?
Yes, because in this case you get a proof that chocolatey equals cheesy, and you can use an absurd pattern to match on that proof. Yes. Okay. So the standard example of dependent type is this type of vectors, which are like lists, but with an extra argument that indicates the length of the list. So it's a dependent type indexed over a natural number, which represents the length. And so here are some examples, right? So we can have a vector of natural numbers, or 4 natural numbers, right? We have to give 4 of them. We can give a vector of, like, of the 0 numbers, but it has to be the empty vector. And we can give a vector of functions as well, right? So here's 2 functions. Okay. So, and again, so this is defined in a very similar way to this type of food that I defined, right? So it's defined as an index data type. So now we're combining a parameter, so the type of the elements, and an index, right? So the index is the natural number. So these are both arguments to vec, but the parameter here appears before the colon, the index appears after the colon. What's the difference between we have the parameter A, right? That is the type that is the same for every constructor, right? So the type doesn't change, while the length can be determined individually by each constructor, right? So each like the empty vector chooses the length 0. The cons for vectors takes a vector of length n as the tail and then produces something of length successor n. Okay.
So you've used the same names for building pods. Those names now overloaded, or do you have only one thing?
Excellent question. That's another difference between Haskell and Agda, which is that we have overloaded constructors, and Haskell should have them too. Yes.
How would you disambiguate between them?
Based on the type, like you know. I mean, if you don't know the type, then you cannot disambiguate, and then you will get an error from Agda if it cannot disambiguate based on the type. But
because in Idris it also supports overloading, then you can disambiguate by doing, for example, vec dot and then.
Yeah, you can also explicitly qualify the name of the constructor if Agda cannot disambiguate it. Yeah. Yes. Okay. Right. So this is what I said. So the argument A, that's called the parameter, that has to be the same for each constructor. The argument of type not, that's called an index, and it can be determined individually, like can have a different value for each constructor. Okay. Question for you. So let's suppose we look at this type of vector of booleans of length 3. So how many elements are there in this type? How many distinct elements are there in this type? 8, I hear, yes. Yeah, so indeed, so these 8 in particular, right? So you have to give a vector of 3 booleans, and there's 8 different ways of doing that, right? There's no undefined, partially defined or undefined elements here because we're in a total language. So these are the only 8 elements of this type. Yes. 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 Yeah, the question is, could you just always use indices? So yes, you could. So I mean, so there is a few subtleties. So one of them has to deal with these universe levels, which is that indices have to be in a smaller universe, while the parameters can be in any universe. But apart from that, you can always treat a parameter as if it was an index. Yes. Okay. Yeah. So then, one thing that might already be clear, but let me point it out explicitly, is that Agda does evaluation of expressions during type checking. So in particular, you can write functions or expressions inside your types, right? So if you have a vector of length 2 plus 2, then Agda will evaluate it during type checking and see, well, if you give it a vector of length 4, that's okay. And so this is one other place where the totality of Agda is, well, if not strictly necessary is at least very useful in that, well, we know that the evaluation will terminate so that we don't go into infinite loops during type checking of our program. And so, I mean, in a non-total language, well, either you would have to deal with the fact that your type checker can loop, or you would have to restrict the type level language to only allow safe expressions for which you do know termination. Yes.
So if you have like the vector pools on the last slide, can Agda case refine into all of these?
I mean, yes, but you have to do successive case splits, right? So if you have an input of type vector of length 3, and you pattern match, well, it will only introduce one constructor per time you pattern match. But if you keep just doing Ctrl+C, you will end up with these 8 cases, yes.
But you can't just go from like no cases to 8 cases.
No. Yeah. You have to keep case splitting, yes. Okay. Yeah. And then if you use the wrong length, you will get a type error, right? This is the whole point, right? That this is statically enforced that you're not using something of the wrong length. And in particular, so in this example, you will see, well, the error messages are not always the best in Agda, I have to admit. But in this case, Agda says, well, successor of something is not equals to 0. And so in this case, well, successor of this weird thing, that's the length that Agda has determined for this vector. And so actually, well, this length should be 2, but it hasn't fully determined the length yet, and it already threw the type error, which is why you get this weird meta variable, so-called meta variable in the type. Anyway, okay. I think I wanted, since this is a 2-hour talk, I wanted to maybe take a 5-minute break and then continue after that. If you have questions in the meantime, feel free to come up here or ask. Otherwise, yeah, let's just refresh our brains a bit and we can continue with dependent functions after that. So we can have enough time still to get through the rest of the slides and hopefully get to the proofs at the end of we actually prove something about some Haskell functions. Okay, good. So now we have dependent types, and now let's see, well, how do you write functions using these dependent types? And these are perhaps not surprisingly called dependent functions. So, okay. So what's a dependent function type? Is a type that has this form where we have a function arrow, but we give a name to the input, and the input can actually appear in the type of the output, right? So that means that type of the output depends on the value of the input. So here's one example of that. If you want to initialize a vector with all zeros, and we give the length of the vector, right? So, and then we return a vector with that n as the length. Well, we pattern match on the number. In the case that it's 0, well, now the type here becomes vector of length 0, right? So we have to return a vector of length 0, which is the empty vector. And in the second case, now we have to return a vector of length successor n, which we can do by using the const constructor with, as the tail, a vector of length n, which we can construct by making a recursive call, right? So by pattern matching on the input, we're actually in each class, we're refining the type in the output. So actually, I was using another dependent function type in some other example, without you realizing perhaps, but so if we defined the identity function, this was strictly speaking also a dependent function because it took an argument of type set and then returned something where the type was dependent on this argument of type set. So any polymorphic function, strictly speaking, in Agda is also a dependent function. Okay. Good. Yeah, and then so there is this thing where we refine the value of the thing that we're pattern matching on directly. But if we pattern match on some index data type, this has this can have some further consequences, not just on the argument we're refining, but on the other arguments as well. And the example here is, well, when we have a vector as an input, right? So we have a vector of length n as an input, where n is some implicit argument, and we pattern match on the vector. Well, this also influences what the number n should be in each of the clauses, right? So here, if we find a map function on vectors, and we are in the case where the input vector is empty, then that means that the length, the number n here, will be 0, which means that, well, then the output should also be a vector of length 0. Right? So here the information is kind of flowing indirectly. We're pattern matching on the vector. This forces n to be 0, and then we know that we can give an empty vector as the output. And similarly, for the second class, we pattern match on a non-empty vector. That means that the length has to be a successor, which means that now the output also can use the const constructor. And so in this way, it enforces that in each of the classes, the length of the input is the same as the length of the output. Okay. And then, so one further thing we can do now is, well, we can actually, instead of giving a vector of length n as an input, we can also say, well, suppose we want to define a head function. Well, we should only apply head to a vector that has length at least once, right? We don't want to apply head to an empty vector. Okay, so we can do that by just saying, well, it has to be a successor in the type of the head. And then we pattern match on it. And nice thing is, again, that now Agda sees, the coverage checker of Agda sees that the empty vector is impossible here, because the empty vector has length 0, the input has length successor, and these two can never be equal. So we only have to define the case for head of a non-empty vector. And the same for the tail function. Yes. Good question. So the question is, what if you wrote n plus 1 in the signature? So it would work if you write 1 plus n, but not if you write n plus 1. Which is because of the way plus is defined. So plus was defined by recursion on the first argument, which means that Agda will only look for evaluating it at the first argument. So if the first argument is a variable, it would not know what to do or how to evaluate it further. And so you will not be able to pattern match on it. Because you will get this error, cannot unify n plus 1 with 0. So...
is 1 plus n definitionally equal to?
The question is 1 plus n definitionally equal to successor of n? Yes. I'm kind of avoiding talking too much about definitional equality here, but yes. Okay. So now, so this is nice. Now we can use head and tail to get the first argument of a vector, we can get the second argument, the third argument, as long as we know that the input vector has at least that many elements. So we can apply all these functions. But like suppose we want to get the nth argument where n is some input, right? Or where I is some input. And we know statically that I is strictly less than the length of the vector. How can we then look up an element at that position? And we really want to get an element of type A as the output, not of maybe A, right? We want to statically ensure that there is an output. And so in order to do that, well, we need one more type, which is this so-called fin type of a finite set, which is so fin n. This is the type of finite numbers. So all numbers from 1 to n minus 1. And so the way it's defined is, well, it's an index data type where the index now indicates the upper bound. Oh, sorry. The index indicates the upper bound of the finite set. And so and each of the constructors kind of enforces that we're always below that upper bound. So I think So there's a nice way to visualize this type of finite sets. Right? So if you have start by looking at fin0, well, both of these constructors have an output of type successor n. So there's no way to construct an element of type fin0, right? So fin0, that's an empty type. There's no constructors there. Then for fin1, well, we can use the 0 constructor because 1 is the successor of 0, so we can use the 0. But the successor constructor requires an argument of the previous fin type, right? So there's no element of type fin0, so we cannot use the successor to construct an element of type fin1. And then for the next layer, for fin2, well, we can use 0 again, but now we can also use the successor of an element of one of the previous fins, which in this case is only 1. So basically how you see that you're adding, each time you're adding one extra argument to the type, which is the 0, or it's a successor of one of the previous elements. Okay. Yes?
Is it possible for those fin types to be optimized down to integers as well? Because in integers, it's notorious that this is not possible for some reason.
The question is, can we optimize these fin elements to integers? Not with this definition, right? So there's an alternative definition, which is, well, you take a natural number together with a proof that it's beneath the bounds. And so that can be optimized, but so Agda only has built-in for naturals and not for fin. I mean, there's no technical reason why it would be impossible to also add a built-in for finite numbers, but there is none. Can you write a function from fin0 to fin1? Yes, there's actually several of these functions. Well, in this case, there's only one because, well, there's no possible inputs, but like in general, there are several ways to embed fin_n into fin1 plus n. Either by shifting up or by... Yes, yes, indeed. Yes. Yes. Let me actually show you. So if we scroll down a bit, so here's the fin type, and so here's a proof that there's no element in fin0. Right? So we can, if we have a fin0, then we can produce an element of any type A, right? By saying, well, using this special pattern. So this is called an absurd pattern. Right? And I mean, Agda will generate it. So if you k-split here on X, then Agda will generate it for you, right? It just means that, well, there's no constructor here. And please make sure that this is actually the case. So Agda will check that none of the constructors are valid at this type. Okay. And so now I want to actually, well, it's good that we're switching. Oh, there's another question, yes.
So the fin and the net are two totally different types.
Yes.
It looks like they have the same constructor, but these constructors are actually totally different data types.
That's correct. Yeah, so the fin and not are kind of unrelated. They're not, it's not a subtype of not or something. So there is this very nice theory of ornamented data types, which says that fin is a kind of an ornamented version of not. So unfortunately, there's no proof assistance with built-in support for ornaments somehow, even though it's a very nice feature to have. I mean, you can encode it in Agda, but then it's, yes, more questions. So the question isn't list. List is a different ornament of a natural number, yes. So which is where you're ornamenting each constructor with an element of type A. But I think fin could also be seen as an ornament where you're kind of adding an index instead of adding elements. Yes. Yes.
I think I remember reading a paper about ornaments where list and fin are ornaments of net, and
Yes.
net is an ornament of, you can either go from fin to leg or from list to leg.
Yes, indeed. So yeah, so both fin and list are ornaments of not, and then you can start from either of those and get vec as an ornament from that. Yes.
I think there's also a question here. How are the constructors for nut and the constructor fin are sub zero sub, right?
Yeah.
Disambiguating based on the type, or?
Yeah. So the constructors, whether suck is a fin or not, is disambiguated based on the type. Yes. So it depends on where you're using it, and then I mean internally there are different names, but Agda, just in the surface syntax they're the same.
Yeah, because in Haskell you can do that.
Yeah. Yes.
So this fin, could I also express it in the fact that it's a NAND, but it's less than n, something like that?
Yeah. So that's there's another way of defining fin, which is as a pair of a number together with a proof that it's less than n. Right, so that's it's an equivalent way of defining it, and there's advantages and disadvantages of using both. Yes, yes. Okay, so let's actually implement this lookup function now. Right, so because we now have all the tools for implementing it. And so, okay, so here's the type signature already. We have a vector of length n, and now we have an index which is valid for this vector. So it's a number strictly less than n. And we want to return the element of type A, so no maybe involved. Okay. So let's do so. Let's try to make use of Agda's case splitting, of course. So which one do you want me to case split on first? We have two arguments. We have an axis or an I. Axis first. Okay, let's do axis first. And so Agda says, well, actually, there's only one case here. We cannot have an empty vector. So there can only be a non-empty vector. We have to look up. Yeah, okay. So now we have this non-empty vector. We have to look up an element. So now we'll also have to case split on I, actually. So let's case split on that one. Right? And then we have to look up, well, the zeroth element of a vector. Well, that's this one, right? So that should be x. And then the suck I, we can look it up. Well, what do we do here? We can just make a recursive call to look up vec with the tail and I. And hopefully here, well, let's actually start. Let's give a question mark here, right? So if you want to look up in the tail, well, we have to give a vector of length n, well, of the length of this one. But luckily, because we also pattern matched on the fin number, now this has the same upper bound again, right? So if successor of I is an index in this one, then I is a valid index for the tail here. So we can actually use the I here. Okay. And so here we end up with a function. And of course, well, we've proven it correct, but we might still try that it actually works. And apparently this lookup vec was a vector of, or this test vec was a vector of booleans, and at position 1 there was false. Okay. I can go to the definition to not show that I'm not.
You mean test vec?
Test vec, yes. I'm jumping to lookup vec. Test vec, true, false, true. Okay, so yeah. That position 1 was true. Yes.
This is probably a stupid question, but I noticed that we were moving around the definition of lookup vec, that the x is the factor here where we have x plus x is.
Yes.
It was highlighted both branches, but of course those two x's have nothing to do with each other, right? Because they're not the same in the situation.
No, indeed.
That's what I mean, yeah.
Yes. But this is VS Code just highlighting based on the name, I think. This is nothing smart of the Agda mode or anything. Yeah, that's correct. Ideally, we would have a proper LSP implementation, and there's people working on that. So hopefully, we'll get a better implementation where it would actually recognize the scoping rules of Agda and only highlights the ones that. Okay. Yes.
So when you were using the holes to fill in the definitions.
Yes.
Can you explain what the response from Agda was actually? What that actually
So when I do this, huh?
So what are we actually looking at? So how does this help us? What this is?
Well, so here, okay, so I have a bunch of holes in this file. So here we have to look at hole number 4 because this one has number 4. Right? So you can see that 4 has to have type A. So you can get more information about the hole by doing this Ctrl-C, Ctrl-comma. And then it will also tell us the bindings that are in scope. So it will tell us there is an I of type fin n, there's an axis of type vec an, there's x of type A, and then there's some implicit arguments which are not in scope, but they're still there for the typing of the other variables. Yeah. Oh. That's not what I wanted. Okay. Yes.
Like this seems like a function that could be automatically derived from either from the first hole. Try to go on.
Yes.
But no, because this could be hacked, right?
Yeah, I mean, so here you could, like, there's other implementations possible, right? This is also a valid implementation of this function. I mean, it's not fully proven correct, right? You can always return the first element. Yeah, right. We don't like you can ask for an individual hole to be filled in automatically with Ctrl-C, Ctrl-A, but there's no functionality like in Idris where it can construct a whole function for you. Yeah. Although that would be cool, but okay. Yes. So here's the lookup function again, which is now safe and it's total, and we didn't have to change the return type. Okay. So that's cool. Okay. Right. So that brings us. So that's dependent types, dependent functions. So that's one way that is quite powerful way to use dependent types to enforce invariance of your programs and to kind of statically rule out the cases where these invariants are not satisfied, which then also gives you extra power when you're pattern matching on the inputs, right, that you don't have to deal with cases that are invalid. And now I want to move on to, well, a kind of a different use case of dependent types, which is actual theorem proving. So the way this works is through this Curry-Howard correspondence. So let's take a look. So the Curry-Howard correspondence, I think, is nicely summarized by this quote by Phil Wadler, who said, well, every good idea will be discovered twice, once by a logician and once by a computer scientist. And so this is also true for many ideas in type theory and logic, which, I mean, kind of the Curry-Howard correspondence says that these are kind of the same thing and that we're just looking at it from different lenses. Okay. And so let's see what that means. Okay. So I'm making a claim here that Agda is not just a programming language, but also a proof assistant. And we want to, that means we can use it to verify properties of our programs after the fact, after we've written the programs themselves. And so these are the kind of properties you might want to prove. Right? So for any x of type not, x plus x is even, or the length of the output of map is the same as the input list, or if you compute the reverse function in two different ways, like an efficient and an inefficient way, well, these are the same. So suppose we want to write down proofs of these facts. Well, we have to think first about the question, well, what does it mean to have a proof of something? Right? What does it mean? It's a very philosophical question. And so the Curry-Howard correspondence gives one quite concrete and practical answer to that, I think. So in particular, Curry, this guy, right, also gave his name to Haskell. He said that we can interpret logical propositions as the types of all their possible proofs. So if we take some proposition from logic, we can just interpret that as a specific type in our type theory. And in particular, that means that, well, since we have false propositions, like, I mean, any good logic should have propositions that are not provable, right? So that means that we should have a type that corresponds to a false proposition, which means that there's no proofs, hence it should be an empty type. And this is a reason why this works in Agda, but not in Haskell, because in Agda we have an empty type. Well, in Haskell, well, we can always use undefined or a loop to inhabit a type. Okay. So this is the first thing we need to actually use this very hard correspondence is we need empty types in our language. And then we can extend this, right? We can think for each of these connectives from logic, well, what does it mean to construct a proof of this connective? So for example, for A and B, well, we can think, well, how do we prove A and B? Well, we have to provide a proof of A and a proof of B. So that means we need a pair of two proofs, right? A proof of A and a proof of B. So this is a pair type. So function type, that's another example, right? How do we construct, or sorry, function implication, I'm going ahead of myself. Implication, so A implies B, how do we prove that? Well, to prove A implies B, well, we assume that A is true, so we assume that we have a proof of A, and we have to construct, from that we have to construct a proof of B. So it's just a function from proofs of A to proofs of B. Right? So each of these propositions very nicely maps to a type in the type systems that we know and love as functional programmers. Okay. So, and that gives us this kind of nice translation between the world of propositional logic and the world of type systems, right? So each proposition corresponds to a type. So that's each proof of a proposition corresponds to a program of that type that was given by the proposition. Conjunction, that corresponds to the pair type, right? We call it P times Q. Disjunction corresponds to, well, how do we prove a disjunction? A or B? Well, we have to provide a proof of A or we have to provide a proof of B, right? So that's an either type, which we can also define as a data type. Implication, that's, as I said, that's a function type. And then we have basic propositions of truth and falsity. That's a truth. And then these are, well, typically denoted by the top and bottom symbols, which correspond to unit type, so which is the empty tuple type in Haskell, which has a single proof, and an empty type, which is a type with zero constructors. Okay. Yes.
Sorry, but this is a little bit of nitpicking.
Yes.
I've been to a proof theory seminar in which the lecturer said that if you have a program of a type that's not actually a proof of proposition, that's a proof object from which the actual proof can be recovered. So proof is the act of inference. The whole process is the proof, and that's why proof object is
I mean, okay, so that's getting a bit philosophical, I guess, in like, is this proof object, is this program itself the proof, or is the proof the process of deriving the well-typedness of this proof? I'm not sure if I agree with that, but I think that will lead us a bit into a philosophical discussion. I mean, I would argue that this, I mean, so you could use a different term for this. You could use the term evidence instead of proof. And then I think your professor would have less of a disagreement with it. Right? I mean, for me, these things are really what I call proofs of a proposition. But so if we were in an extensional type theory, I would agree that the proof terms themselves are not enough to establish the truth of a proposition, because there it's undecidable. But here, because type checking is decidable, we can always reconstruct the typing derivation from just the proof object. So the proof object itself is enough to get back the whole process of deriving the proof. Yes.
Is there a reason why Agda chose the X, so multiplication symbol for the product type, but either and not plus for the sum type?
No, actually, so So actually, this is not what the standard library does. So in the standard library, it uses the U plus symbol, so the disjoint union symbol for either. I just hadn't introduced it yet, so I just wanted to rely on your Haskell knowledge here and use either, but yeah. Yes, more questions?
In practice, how does writing proofs for finite types compare to writing proofs for limited what you can do with infinite types? Coordination checks, or are they in practice?
So the question is, are you more limited to proving things about infinite types compared to proving things about finite types? Well, so far I'm not proving anything about types. I'm just proving pure propositional logic to type systems, right? But in general, there's not much of a difference between the two. Like you can just as easily prove things about an infinite type of like not as finite type like fin. It's not much more difficult. Like there's no special new things you have to deal with it. Okay, let's have another quiz question. So suppose I'm giving the proposition, well, if P implies Q, then P or R implies Q or R. I think that's a valid proposition. So the question is, how do we state that in Agda? Suppose we want to prove this. Who thinks this is the first one? Who thinks this is the second one? This is the third one. Oh, and the fourth one. Okay, you're much more smarter than my students in Delft. Okay. Yes, indeed. So if P implies Q, then well, this or is translated to either. So P or R is translated to goes to Q or R. Beautiful. Okay. So and then let's take a quick look at some of the basic proof principles and see how this translates to Agda functions. So maybe the most basic proof principle is modus ponens, which says that, well, if P implies Q and P is true, then Q is true. So if we want to prove this in Agda, well, we first translate this statement to a type, and in order to prove it, we have to construct a program of that type. So in this case, well, we know that P implies Q and P, right? So there's I'm writing it in uncurried form here. You could also write it in curried form. That doesn't really matter, but so we have a proof that P implies Q and a proof of P, and all we have to do is just apply the function to get the proof of Q. Okay. So this modus ponens is just a function application. Let's take a look at another example. So proof by cases is the principle that, well, if we know that P or Q is true, and there is some proposition R which follows from P, and R also follows from Q, then we can prove R. And again, we can prove this in Agda by saying we have a proof of either P or Q, and we have two functions from P to R and from Q to R. And so the way we're proving it now is, well, we pattern match on the proof of either PQ, right? And so we have two cases to deal with. Either we have P is true, then we apply the first function, or Q is true, and then we apply the second function. Right, so here we're using pattern matching in order to prove something by cases. Okay. One more example is a principle of explosion, which is if we assume that something false is true, then we can prove anything else. So also known as ex falso quod libet, by the way. So how do we prove this in Agda? Well, we first need some type to correspond to the false proposition. So that's this so-called bottom type, right? That's a data type with 0 constructors. And then to prove, well, we can prove any proposition P from that. So you write a function from the empty type to P. And so to do that, we use this absurd pattern, saying, well, there's no possible constructors. So you can just skip the right-hand side for this clause. Okay. The absurd pattern, is that something that's hard-coded? Well, in a sense, yeah. I mean, it's the syntax of Agda. So, I mean, the way it it checks that it's empty is just by trying to enumerate all the possible constructors, and in each of the cases it will derive some kind of absurdity from the type constraints. So, and then if it's left with no possible cases, then it will accept the absurd pattern. Okay. And then we can derive some, other logical notions from this, like we can derive negation as being a function from P to the empty type. And we can define logical equivalence as well as a pair of functions from P to Q and from Q to P. Okay. I have some exercises here, but I also really want to get on. So I think I'm going to skip those, but you can try these at home if you want. And I have a lot more of these, by the way, if you want more, then it's great fun.
Equivalence, does Agda also have a separate type for equality?
I'll get to that, yes. Okay. So if you want to do these at home, you can find them in the lecture notes. Or, anyway. Small side note here is that, the logic that Agda is using is not classical logic, but it's constructive logic. And that means that there are certain so-called non-constructive statements that we cannot prove in Agda. And these are statements such as the excluded middle, so P or not P for some unknown proposition P, or double negation elimination, which says that not P implies P. And so the reason why we cannot prove this in Agda is, Agda has a constructive logic, and in particular that means that to have a proof of A or B means that we have a decision procedure to really determine if A is true or B is true, right? And so if we get an arbitrary proposition P, we don't have this decision procedure, so we cannot prove P or not P. So people sometimes complain about this, and I say, oh, you cannot prove these things, and these are really needed to do mathematics. So luckily, there is, a long time ago, these two great people, Gödel and Jensen, came up with a way to embed classical logic in constructive logic. So there's actually no loss of expressivity. And the only thing you have to do is just add two negations at the start of your proposition. And then they proved that, P is provable in classical logic if and only if not P is provable in constructive logic. So that's, so actually that means that, instead, rather than being weaker than classical logic, actually constructive logic is more precise or more expressive because it can actually make the distinction between these two statements, while classical logic cannot make a distinction. And fun exercise here is to prove the double negation of double negation elimination, which, according to this theorem, it should be, you cannot prove this one, but you can prove not of not P implies P. So that's propositional logic. Let's move on to predicate logic, right? So we want to not just write abstract propositions, but we want to write things that, predicates that say something about our programs or about the inputs and outputs of our program. And so, for example, let's say we want to define a predicate that says that a given number is even. How do we do that? And the answer that Agda gives us is, we can just do that, define that proposition as an index data type. Right? So we can define data type is even of proofs that the given number, which is an index, is even. Right? And then the constructors give us the different valid rules for deriving that a number is even. Right? So in this case, there's two ways to derive that a number is even. Either it's 0, so 0 is an even number, or if we can derive that n is even, we can also derive that successor of n is even. Right? And then indeed, we can prove that 6 is an even number by applying this second constructor 3 times. And we can also prove that 7 is not an even number by pattern matching on this constructor a few times until we get to the absurd pattern. Okay. Good. So just as a small sanity check to see that this is really something that is expressing evenness of the number n. Yes. The question is, why can't we just write the empty brackets here at the top level? Well, yeah, so indeed. So you actually do have to do the pattern matching to the point where Agda, it's obvious enough to Agda that there's a contradiction. So, yeah. So Agda will just check locally that there's no contradiction, but it will not deeply pattern match on the arguments to derive contradictions. You have to do it by hand. Because otherwise, I mean, it wouldn't know how deeply to pattern match, right? Okay. So in general, defining a predicate in Agda looks a bit like this, right? We define a data type that takes something of the base type as an index, and then each of the constructor expresses the different ways to prove that this predicate is satisfied. Okay. And then we can, for example, prove, well, if you have this double function, we can prove that for every number n, the double of n is even, right? So this is a universal statement, right? So this is a for all statement. And so the way we formulate it in Agda is by using a dependent function type. So we could take our table that we had before and say, well, a universal quantifier corresponds to a dependent function type in Agda, right? And that's just mapping each element of type not to a proof that double of n is even. And so in order to prove it, well, we just pattern match on the number, and we use the appropriate constructor, and then we make a recursive call. Right? So it's that easy. So in general, so again, so if you want to prove a predicate like this or a dependent statement like this, well, this is a proof by induction on natural numbers, right? So we have to pattern match on the number and then give a proof for the zero case and give a proof for the successor case. And then while constructing the proof for the successor case, well, we can use the fact that it's already proven for n by making a recursive call. And so here it's really crucial that the termination checker is running because we only want to use the proofs for cases that already have been proven before, right? So it has to be terminating, otherwise this would not be a valid proof. Okay. And I mean, so in general, there's a kind of a rule of thumb if you want to prove something about a function. Often, not always, but often it's good to try to follow the structure of that program that you're defining, right? So if you had a function defined by pattern matching, well, you want to use pattern matching in your proof. If you have something that's defined recursively, probably you want to prove it by induction, so by making a recursive call to the proof itself. Okay. And so yeah, like as I said, so totality is really crucial here, right? So to ensure that our proofs are actually valid proofs, right? So we cannot skip any of the cases in our proof, and we cannot have circular arguments because of the termination checker. Okay. Yes. Question. I mean, I'm not sure if I have a heuristic for it. So I'm not sure if I get the question completely, but yeah. Yes. Oh, okay, so the question is, when do you have some invariant that you encode intrinsically in the type, or you encode extrinsically as a separate proof? That's a very good question, and I don't think there is a general consensus on that. So I think in other proof assistants, like Cockx or Lean, in general, people only use the extrinsic style with proofs being separate from your data. I mean, so the advantage of doing that intrinsically, like I did for the vectors, is that, well, you don't have to write a separate proof, right? You just write a function and you have the proof. You don't have to repeat the pattern, the same pattern matches again, right? The disadvantage is, well, you have to think carefully in advance, well, which invariants do I actually want to enforce? Because they're already part of your data type definition, right? And if you think later of another property that maybe you wanted to add, then maybe it's too late to add it everywhere. So it's giving up some flexibility in exchange for the ergonomics of not having to write separate proofs. And yeah. Yes, John?
So you showed this nice example where you find double non-natural numbers and then double complex or even.
Yes.
Suppose I had made the rookie mistake finding double n in n plus n.
Yes.
Then I would really be in trouble, wouldn't I?
Oh, good question. So what if you had defined double not like this, but as n plus n? I mean, you would not be in trouble. You would have a bit more work to do, right? So I admit I chose this example kind of specifically to be very easy. So if you have n plus n instead, well, you would have this problem that you have a successor on the right argument of your plus. So you have to prove that n plus successor n is the same as the successor of n plus n. Right, and then use that proof in your, use that lemma in your proof.
So that is the kind of thing that happens to me all the time.
Yes.
And yet somehow you guys managed to avoid that.
No. Oh. So the question is how to avoid these kind of things, and I'm not avoiding these proofs, these things. I mean, I'm avoiding them in these lectures because I don't want to answer difficult questions, but no. I run into these problems all the time, which is why I'm working on Agda and improving it. But
So
so
a risk might be to say, don't reuse plus to define.
to use plus, yeah, maybe.
So don't reuse code. Then you're going to be. That doesn't really sound like a good general
Yes.
advice.
Yeah, no, and I. So yeah, the question, the advice should be don't reuse code, but that is indeed. So I think, yeah, there is a real problem with dependency type languages as they are currently, which is that they are, in a sense, very anti-modular because they rely overly on the computational behavior of the functions you have defined. And so what you would ideally want is some kind of language where you could make abstraction over the computational behavior and say, well, okay, and I know for plus, for example, I wanted to compute on both arguments, right? So there have been some experiments in that way. So myself, I implemented rewrite rules for Agda, so you can actually say that. But there are some very hard theoretical problems to work out there to make it actually satisfy the kind of properties that you want to satisfy, want to be satisfied in a type theory. So there is, yeah. So I would say people are working on it, but there's a big tension between having a simple type theory that's as simple as possible, so we can really know that it's correct and sound, and having the ergonomics of having the ability to write easy proofs. I think, so for me, that's one of the most interesting directions of research in this area. Yeah. But I don't have a great answer to it. Yeah. Yes. Yeah. Yes.
So I'm a little bit stuck on the scaling is not even. How does Agda know that there's no way to get to?
The question is, how does Agda know that certain cases are impossible? The answer is read my PhD thesis. No, but the very short answer is there's a unification algorithm that Agda uses to unify the indices that are declared in the type of your function with the indices of the constructor right? And this unification algorithm, if it returns a negative success, right? If it sees these two things cannot be unified, then Agda knows this is a case that's safe to skip. No, so indeed. So that's why you use proof-relevant unification algorithm, which actually returns the proof that it's impossible, right? So that this case, even with other functions, that it's still impossible. So, yeah. Okay. Another question, yes?
Is it possible to define something like an axiomatic proof of something you can't, for some reason, derive inside the type system, but for another proof you are constructing, you know it's true and you can assume it anyway?
Yeah, so the question is, is there some way to make an assumption that it's something you haven't proven, but you want Agda to assume it's true, or you can postulate it. So there's a postulate keyword, and then you add some axioms to your theory. Or you can add a parameter, right? So you can add a module parameter saying, well, there's an assumption, this whole module assumes that there is some x of some type, right? And then when you import that module, you can actually specify, oh, actually here is the proof, and now fill it in. Yeah. So those are the two main ways to do it, right? So the postulate you cannot fill in later, it's just an assumption. If it's a parameter, you can actually fill it in later when you import that module. Okay. I don't know if you want me to stop now, because I'm officially out of time, but I can also try to do the last part in maybe 10 minutes or so. Yeah, exactly. So it would be a shame to stop now, I think, but okay. Yeah. Yeah, absolutely. Yeah. I mean, of course, it's however you want. I'm here for you. Yeah.
So the next session will be at 3:30. Yeah. And I would say who wants to stay stays, and I guess latest in about 20 minutes or so.
Yeah. Okay.
Is that okay with everyone?
Okay. Maybe I should have expected so many questions, but yeah. Okay. Anyway. So yeah, let's actually go. Let's prove some equalities, and one more of our forefathers, Donald Nutt, had this nice quote. Well, beware of bugs in the above code. I've only proved it correct, not tried it. Was one of his textbooks, The Art of Computer Programming. I mean, it makes sense that he wrote it because he only proved it on paper. But ideally, we want this to be. We'd want this to be an absurd statement, but if we prove something, then it should really hold, right? And we shouldn't have to try our code. Right. So if there's a proof, then it should be true. So let's try to actually prove things about our Agda code. And so, in particular, we want to prove that two expressions really will evaluate to the same result. And so for that, we'll use this identity type, which is the type that expresses, well, equality of two elements x and y. Right? So the type x equals y with the triple equal sign expresses that x and y are equal. And the way it's defined is, well, it's an index data type, just as the previous types we saw, with two indices in this case, right? So two indices of type A. And the only way to prove it is if they're actually the same. Right? So we can only prove that something is equal to something if that something else is the same thing as the thing we want to prove it's equal to. Right? And so what does it mean to be the same? Well, it's not quite syntactic equality, right? Because as you remember, Agda does computation during type checking. So that means that Agda will accept raffle as a proof as long as the two terms evaluate to the same normal form. Right? So if we want to prove that 1 + 1 = 2, well, we can just write raffle, and Agda will compute both sides and say that they're the same. Okay. And so even just this definition already is quite handy sometimes. You can use it to write test cases of your functions, right? And in particular, these test cases are checked each time you type check your program. right? So you can write, well, for example, the length of this list should be 1. And then you just write raffle. And then when Agda type checks this raffle, it will compute the normal forms of both sides and see that they're equal. So, I mean, often you would maybe want to write these test cases in a separate file, and so that, especially if they're expensive, but it's a nice way to enforce that you don't accidentally break something in your code. Okay. But that's only the very basic thing we can do with identity type, right? We can use it to make more general statements as well about our functions. So for example, we can prove that not b equals b for any b. Right? So again, we're using a dependent function type, saying, well, for any b, we can return a proof that not b is equal to b. And the way we prove it is by by doing case analysis, which is expressed by pattern matching on the Boolean. And in each case, well, if the Boolean is b, then not true evaluates to true. If the Boolean is false, then not false evaluates to false. So you have the proof. One more question. So this one is, I think, this is the one that tricks up most of my students. So let's see if you really are smarter than my students. So there's this expression, lambda b to b equals true. And the question is, what is the type of this expression? So who thinks it's a function from bool to bool? Who thinks it's a function from bool to set? Quite a few people. Who thinks it's a function from taking a b of type bool, returning a proof of b equals true? Also a few people. And who thinks it's not a well-typed expression? Yeah. So the correct answer here was the answer 2, right? So this is a function that takes a Boolean as an input and it returns this thing b equals true, right? That's a type, right? So it's returning a type, hence the return type should be set, right? As you saw here, right? So this equality type returns a set. So if you write this lambda expression, then we're returning a set. So this type is type bool equals set, bool to set. If we wanted to write a function of this type, well, we have to give a proof. I mean, and actually we wouldn't be able to write a function of this type because not every Boolean is equal to true. Okay. Okay. And then I think the true magic happens when we actually consider pattern matching on this identity type, which well, we can use to write functions or proofs that assume that two inputs are equal. Right? So here's a basic example. So suppose you got into some messy situation. You have a vector with some very complicated length expression, but actually you can prove that it's equal to some simpler expression. And you want to convert your messy vector to the simple vector now. Well, you can do that with this function, castVec, which takes a proof that the two lengths are equal and converts the vector of the one length to the other length, right? And the way we prove it is just by pattern matching raffle, which will, well, when we pattern match on the raffle, well, Agda will use this unification algorithm, right? It will unify x and y, and it will come up with a solution, well, that these two should be the same. And then once they are the same, well, these two types will become the same, so we can just return the vector x's. Okay. Yes?
It's also worth noting that this is the functoriality of vector A.
This is the functoriality over...
the mapping from the
yes.
category to...
Sure, yes, indeed. So... If we pick the right categories, then I'm sure this is a functor, yes. John, yes.
So in this case, m and n are variables. So it's very easy to understand what you mean by unification to the instantiate m to n.
Yes.
So they could be general expressions in both cases, couldn't they?
So the question is, what if m and n are not just variables, but general expressions? Well, yes. So, but the point is that when you define this function, you define it in the most general case where they are just variables. And then when you define it, unification is easy. And then you can call it with arbitrary other values for m and n. Right? So when you call it, they don't have to be variables anymore. And then you cannot just pattern match on it directly. Then you have to do something. So if you don't have a variable on either side of the equation, then you have to, either apply some other lemmas to simplify the equation, or you have to generalize a statement of the thing you're proving to something where one of the sides is a variable. Right.
So that means in that case, Agda will not allow you to pattern match.
Indeed. Agda will only allow you to pattern match if the unification actually succeeds. Okay. So using this pattern matching, we can prove some other useful properties of equality, such as equality is symmetric, right? So if x equals y, then also y equals x. And that's easy because there's only one case where both of them are equal, so then there's no question. And we can also prove congruence, which is another useful law that says, well, if we have a function from a to b and we know that x equals y, then f of x is also equal to f of y. Okay. And again, just pattern matching on REFL is the proof, basically. Okay. So now for the final part, so we have this, we want to write down proofs about functional programs. And the way we'll do this is by using equational reasoning. And so equational reasoning is what you learned in school, right? So to write down proofs of equalities of arithmetic expressions like this, just by taking a small step in each case. Oh, there's a question. Yes. So how can Agda type check this if it cannot evaluate f of x? Well, it doesn't need to evaluate f of x because you can pattern match on the proof of x equals y, right? So then x and y become equal, and then f of x is the same as f of x. That's just reflexivity. We don't need to evaluate the f of x any further because the two sides have become equal already.
So you're unifying normal forms in which f is a variable.
Yes. Indeed.
Another way to think about this is that the REFL after the equals is basically proof of f of x equals f of x, and we use the first REFL to rewrite that into f of x equals f of y. That's my understanding from using this in
Yeah, so it's not exactly my understanding of what's happening here. So it's you're using the x equals to y to rewrite the proof of fx equals fx to prove of fx equals fy. Not sure if I get the question. So the way I think about this is, well, maybe a bit technical, but there's this so-called J eliminator, which is the basic induction principle for the identity type. And so all of these pattern matches are just special cases of the J rule, which says that if you can prove something about equalities that are reflexive, then you can prove it for any equality. More or less. It's very rough, but yeah. It's a kind of an induction principle for equality proofs. So here we're really proving this by induction on the equality proof. Yes, one more question. Does this lose the referential transparency of the function? I don't see how. Yeah, I don't know. I don't think so.
Yeah. Well, I think f needs to be referential transparent because if f had some side effect, if it had some hidden state.
Oh yeah, so sure, yes. The function f here has to be pure and has to be, yeah. has to be a pure function. Otherwise, this doesn't work, right? And that's true. So we're very much relying on the fact that Agda is a pure language here. Yes. Yeah. Okay. So, okay. Let me try to get to the equational reasoning. So suppose we have this definition of reverse function, and we want to prove that reverse of the singleton list is a singleton list X itself, right? Well, on paper, we would write something like this, maybe, right? We can reason on paper about functional expressions in our language, just applying the definitions of these various functions, applying the second clause of reverse, the first clause of reverse, and then applying the concatenation. And so this proof, we can actually, instead of writing it on paper, we can write it in Agda, and then it looks like this. So this is a proof that reverse of a singleton list is a singleton list. And so almost look the same as what we wrote on paper. So we have a bit of extra syntax here. So we have this begin keyword, an end keyword, and then between the equations we have this equals with angle brackets. And then we just write each of the intermediate steps, and Agda can figure out all of these, that all of these steps are valid. So we now have a proof of the equality in Agda. Now, so this is a very verbose proof. So in this case, actually, a much simpler proof would be to write ruffle, but and that would also be accepted. But I mean, to kind of demonstrate, you can write down the same proof that you would write down on paper in Agda, and it checks the validity of each step. Yes.
I've seen versions of this with some code between the angle brackets.
Yes, so that's indeed. So the angle brackets are there because sometimes you do have to write some justification for the step. In this case, Agda can figure out all the steps by reflexivity. Right? So we don't have to provide any proofs between the angle brackets, or we could write ruffle between the angle brackets. But in general, we have to write, something more. Yes. So this is equational reasoning. So we start proofs with begin, we end proofs with end, and we have these equality signs with the angle brackets in between. And actually, so all of this is just functions, like the syntax defined in Agda. There's nothing special built-in magic of Agda. It's just functions. And so in this case, we could just have written ruffle, but these proofs by equational reasoning are at least much easier to read and often easier to see, well, if something is wrong in your proof, well, where exactly does it go wrong? We can combine these proofs by equational reasoning with the other proof principles like case analysis or pattern matching. So here's the proof again of not B equals B, but now with equational reasoning proof. And we can also use it together with induction. So and here's an example where we actually have to provide some evidence for one of the steps. Right? So what we're trying to prove is n plus 0 equals n. And so in the case for when the n is successor of some number, well, we can apply the definition of plus, and then we have the successor of n plus 0. Now we want to use the induction hypothesis to rewrite this n plus 0 to just n. Right? So that's what we do here, right? Between the angle brackets, we write the induction hypothesis, but then we have to apply it underneath the successor constructor, so we have to use congruence successor with this induction hypothesis. Okay. Okay, and so there were 3 examples I wanted to show. So, okay, maybe I can do one of them. So you can choose which one. So the first one was doing proofs of functor loss of some. So you can use this to prove that your type class laws are actually holding for a specific instance that you're giving. The second one was proving correctness of the fast version of reverse that uses an accumulator. And the third one is proving correctness of a compiler.
Which compiler?
You'll have to ask. And then, okay, I'll do the third one. Let's prove correctness of a compiler. So the language is Hutton's Razor. So this is the super simple language, right? So we have 2 expressions. We have numbers and we have plus. We don't have variables or anything, right? And so we can write down expressions like this. So this is 2 plus 3 plus 4, right? And so we can easily write an evaluator for this, right? We can evaluate, well, each expression to a natural number, saying, well, value is just the number itself. And to evaluate the addition, well, we evaluate both arguments and we add them together. Okay? And so now we want to implement a compiler for this language. We want to compile it to a stack machine. And so this stack machine has 2 operations. So either it can push an argument to the stack, or it can do an addition operation on the 2 top elements of the stack. Right? And so we have these 2 operations here. And then we have a stack, which is a list of natural numbers, right? Where the head is the topmost element. And then the compiled code will be a list of operations. Okay. So for example, for this program, well, the compiled code would be push the number 2, push the number 3, add them together, push the number 4, and then do another addition. Okay. And then given some code and an initial stack, we can compute the final stack. If there's no more code, we just return the stack. If there's a push, we add it to the stack and continue. If there's an addition and we have 2 numbers, we add them together. If there's an addition and there's not 2 numbers, well, we're in an error case. We're doing the thing that John told me not to do, but we're returning an empty list here. So in my defense, this is also how the example is defined in the book Programming in Haskell. So, and just copying it from there. Okay. And then we can write a compiler, right? So we take an expression and we compile it to a list of operations. And it turns out it's nice to write this compiler using an accumulator for the code that we already generated. So we have a compiler that takes the accumulator, and then the final compiler will just start this with an empty list, right? So for a value, well, we just add a push instruction, and for an addition, well, we first compile the first expression, we compile the second expression, and then we add an addition on top of the stack. Or rather, the other way around. We add an addition instruction, but then we first need to push the 2 numbers to it. Okay. And then to prove correctness, well, what do we have to do? We have to prove that executing the compiled code on an empty stack is the same as pushing a single number to the stack, which is the result of the evaluator, right? And so the way we prove this is equational reasoning, and with some lemmas and induction proofs. But so basically, we need a lemma, basically saying what does this comp prime, so this function with the accumulator, do. And so it turns out that that this is the same as doing this, and then we have a single. Then we have no more instructions left, right? And we have to see, well, what does exec do then if the instructions are gone? Well, we just have the stack itself, and that's the end result, right? So the main proof is actually this comp prime exec eval function that says, well, if we have an expression, we have a stack, and we have some code, then we can do 2 things. We can either run our compiler prime, right, on the expression, or we can immediately evaluate the expression, push it on the stack, and run the rest of the code on that. Okay, so this is kind of the crucial lemma that we have to prove for the correctness. And the way we prove this is by induction on the expression, right? So if it's a value, then you can see that compiling the expression is the same as pushing it, and then executing the push is just having the number, right? So this is kind of the base case, which is trivial, and then that's the same as evaluating the value again. And this is the case for the addition, where, compiling the addition, that was this thing, right, where we have make 2 recursive calls and then have the addition on the stack. And that means, so because we have 2 recursive calls, well, we have to follow the structure of our function, right? So we have to apply 2 induction hypotheses. So first for the outs, so first for the inner, yeah, we first apply it for the inner one, right? So for the for the outer one, sorry, for the E1, so the E1, that gets evaluated and pushed to the stack, right? So from here, it goes to here. And then for the E2, we do the same, so that also gets pushed to the stack. And then we have to execute the addition, which is, that's the definition of the evaluator, saying addition with these 2 elements on stack is the same as pushing the sum to the stack. And that's it. Yes.
So when you're writing this proof,
yeah.
how much of this can Agda fill in for you?
How much of this can Agda fill in for you? I mean, so it will not automatically introduce the equational reasoning syntax, right? So you have to kind of...
Okay, so suppose you use equational reasoning syntax with holes.
Yeah, yes. Yeah, so usually I write this kind of proofs by having, I write a beginning and end keywords. I write one step with a question, with some question marks, and then I refine from there.
Yeah. So for example, if we look at the second step there, that's the first step where you use the induction hypothesis. I can imagine you might like to say, okay, here's how I'm using the induction hypothesis.
Yes.
Here's my justification, but then get the following one automatically.
Yes, so you can do that. So there is actually, so if you write down the proof of one of the steps here and you want to get the next line, there is another command that I didn't explain, which is Ctrl+C, Ctrl+S. That will solve all the holes that can be solved by unification or by type checking. And in this case, well, having the proof is enough to know what it's proving it to be equal to, so that will fill in that hole for you, yes. That's quite a useful thing to do sometimes. Yeah. Okay. Yes.
So I noticed that you're basically proving some property of Agda functions,
yeah.
but you also proved some property of Haskell functions because the function that you proved something about, they didn't use any dependent types. They basically look like Haskell functions.
Yeah. So yeah, indeed. So the functions that I wrote here are really just copy pasted from Graham Hutton's book. So they are just Haskell functions written in Agda syntax, yes.
And proving something about Haskell functions is exactly what I want to do.
Yeah.
Is there any prior art?
Let me advertise my tool that we're working on, which is called Agda 2HS, which allows you to implement Haskell functions using Agda syntax, prove things about them, and then extract out the Haskell codes from that, right? So it will erase all the proofs and all the dependently typed stuff, and we'll just end up with the simple Haskell function. Yeah. That's the whole goal of that project. No, we have not proven correctness of Agda 2HS yet. It's a bit. I mean, we want to do it, but it's a bit hard because. Well, it's translating from Agda to Haskell, and we don't have a good semantics of Agda, and we also don't have a good semantics of Haskell. So it's like, what are we even proving? I don't know. Yeah. Yes.
For example, if you have a value of type back for NAT in Agda, what would the output type on the Haskell side be?
So if you want to use Agda 2HS with index data types, you have to mark the indices as being erased. So otherwise, Agda 2HS will reject it. And so in that case, it will just compile down to basically something isomorphic to a list type. Yeah. So the index will be gone. So there's an open issue to also add support to actually generate the GADT, but that's not supported yet. Okay, let me conclude because I see, we're running out of time. So summary, Agda is a pure functional language, not too dissimilar from Haskell. But it has dependent types, which you can use to statically enforce all kinds of nice properties. And it also has, well, it's a total functional language, which means that you can use the Curry-Howard correspondence. And so in particular, you can express propositions as types and their proofs as programs in Agda. If you want to learn more, well, this was based on my lecture notes that I used for my functional programming course. There's a lot more details and things I skipped over here, so go read those. There is some introduction also in the official user manual of Agda called A Taste of Agda, so it's another thing you can read. There's a quite nice textbook, online textbook, freely available, called Programming Language Foundations in Agda. So particularly if you want to do PL theory in Agda, I think it's a very good introduction, but otherwise it still kind of gives a nice introduction. And there's this tool, Agda 2HS, that I talked about. Okay. And then very finally, I want to take like 30 seconds to advertise that I have a PhD student who recently started, and she really wants to do research on usability of interactive theorem provers. So if you're a user of Agda and you want to help with that research, you can scan this QR code. I'll also post it to Discord if you want. And sign up. She wants to interview people who actually use these tools and to see like what are the biggest usability concerns and how could this be improved? Okay. That's it. Thank you very much for your attention. I'm sorry for going so much over time, but I really enjoyed this, so thanks.